Bonsoir, madame. Bonsoir, mesdames et messieurs. D'abord, j'aimerais vous remercier de votre présence. Je suis ravi d'animer cette rencontre avec M. Alan Bernstein, qui est président et chef de la direction de l'Institut canadien de recherche avancée. Comme vous le savez peut-être, je suis un ardent partisan de l'Institut et membre de son conseil d'administration. For more than 30 years, CIFAR has been connecting Canada's and the world's best researchers. We bring them together into collaborative, interdisciplinary programs and ask them to tackle questions of importance to the world. Our researchers have made important discoveries in areas as diverse as population health, the genetics of disease, artificial intelligence, and the beginning of the universe. Today, CIFAR has 360 researchers from all over the world, grouped together in 14 different interdisciplinary programs. CIFAR plays an important role not only in advancing knowledge, but in sustaining Canada's global research leadership. Je suis particulièrement heureux de voir tant de gens du milieu de la recherche du Québec. Nous sommes réunis ce soir pour célébrer 3 réalisations scientifiques particulières où des chercheurs basés au Québec se trouvent à l'avant-garde de percées mondiales. Many people in the room tonight have worked hard to make these successes possible, and among them are the members of CIFAR's Board of Directors. In fact, CIFAR held its board meeting here in Montreal today, so we have a number of directors in attendance tonight. And I'd like to take a moment to introduce each one of them. And as I call your name, my friend directors, could you please stand? Jim Denning, David Dodge, Pierre Ducros, Brenda Eaton, Lindsay Gordon, Stephen Lister, Pat Meredith, Bruce Mitchell, Lawrence Pentland, Barb Stymius, our chair, and Bill Young. And thank you all for your tireless work, which is so vital to sustaining CIFAR for decades to come. Au fil de la soirée, je vous encourage en fait à échanger sur l'ICRA et le travail que nous faisons avec les membres du Conseil qui partagent votre table. CIFAR has been undergoing significant transformation in recent years, and the driving force behind this has been its president and CEO, Alan Bernstein. Dr. Alan Bernstein has spearheaded a dramatic new vision for the organization. Among other things, he instituted a global call for ideas that led to a 25% expansion in its research portfolio. Alan has also increased the Institute's focus on connecting researchers with those in medical practice or policymaking or industry, who can turn knowledge and insights into actions that have impact on our world. Également, sous la gouverne d'Alan, et grâce au généreux soutien de la Fondation Azrieli, nous avons récemment restructuré notre programme destiné aux jeunes chercheurs. Et nous sommes en train d'organiser un forum où se réuniront des experts mondiaux de la recherche sur le bien-être de l'enfant, qui aura lieu au mois de novembre 2016. Alan est lui aussi un chercheur qui a plus de 225 publications scientifiques à son actif et qui a fait des contributions importantes à l'étude des cellules souches et du cancer. Il a été directeur général de la Global HIV Vaccine Enterprise et président fondateur des Instituts canadiens de recherche en santé. He is a senior fellow of Massey College and is an officer of the Order of Canada. Last year, he was inducted into the Canadian Medical Hall of Fame. Je vous prie d'accueillir le Dr. Alan Bernstein.
Thanks, Jean.
It's all yours.
Merci. Merci, Jean-Guy, and thank you for your very nice introduction and your opening remarks, and for the work you do for CIFAR. It's really wonderful to be in Montreal tonight, and I think this is a great follow-up on a long but very exciting day that we had at our board meeting here in Montreal. J'aimerais maintenant vous souhaiter la bienvenue à cette soirée. Nous sommes ravis d'être parmi vous ici à Montréal. Quelle belle suite à une journée riche en discussions. This is, I think, truly an extraordinary time in science. From last month's exciting discovery of gravitational waves, which Victoria Kaspi might tell you about, which provided the very first experimental evidence of Einstein's general theory of relativity, to CRISPR-Cas9 technology, which is genome editing and has the power to detect, if you will, a single letter mistake in a 900-page book and to correct it, to artificial intelligence, which I'm sure Yoshua will talk about later on tonight, and smart cars. The pace of science has been extraordinary, extending humanity's understanding of the world around and in us and the cosmos in which we live. Now, when I was a boy, I dreamt of sitting in the front row of the Montreal Forum to watch Beliveau and Rocket Richard and Guy Lafleur play hockey, of course. Unfortunately, that dream never came. Now, I'm still a boy at heart, if anybody wants to correct that mistake, but today as president of CIFAR, I truly have the privilege of having the very best seat in the House, to watch the very best scientists in the world do what they do best, which is to advance our understanding of ourselves, the society we create, the world around us, and the cosmos that we inhabit. And from that understanding, we know from the past 300 years of science will come better, wealthier, healthier, and more fulfilled lives. So tonight, all of you have a front seat. Seated at most of our tables is a CIFAR board member and a CIFAR fellow. And so I hope you'll take the opportunity to discuss with our board members where the Institute is now headed, and with our researchers how CIFAR contributes to the research that they do and their views of where science is going. I'm also especially delighted to extend a special welcome to the Azrieli Foundation and to the family, Mrs. Azrieli and Dr. Azrieli, who are in the audience here with us this evening. Through the Azrieli's Foundation's great support, the largest gift CIFAR has ever received in our 34-year history. We have been able to significantly enhance one of our new research programs and to launch, just last week, the new CIFAR Azrieli Global Scholars Program, a very exciting new program for young scientists, which we're both very excited about. I'd also like to acknowledge many other generous donors that are here with us this evening. I can't single out everybody, but I will single out the Power Corporation, the Trottier Family Foundation, and the Howard Webster Foundation. I believe that we live in a time when organizations like CIFAR are needed more than ever. It is research, and research alone, that gives us hope and can address the complexity and the magnitude of today's opportunities and their challenges. Climate change, the refugee crisis that we see all too often on our TV screens, terrorism, social inclusivity, economic development, child and brain development, the health of our oceans, the genetic basis of disease, all of these challenges and many more They demand the collaborative effort of the world's very best researchers, regardless of discipline, regardless of institution, regardless of country. And that is precisely what CIFAR does. For more than 30 years, we have been connecting Canada and the world's best minds in unique global research programs to address questions of importance to the world. There is no other organization like CIFAR. We give our fellows and advisors, who are based in 115 institutions in 18 countries, the time and the freedom to explore new perspectives, new collaborations, and explore new paths to discovery and paradigm shifts in ways of thinking. CIFAR creates the unique conditions that make it possible for our fellows in widely divergent fields to have deep conversations, to learn from each other, and to collaborate with each other. Over time, our fellows shape entirely new ways of understanding, and you will see three, I believe, outstanding examples tonight. Our work puts Canada at the very center of the world's most important global conversations, and those conversations ultimately lead to transformative knowledge that will change the world. CIFAR makes Canada's best better. Throughout CIFAR's history, Quebec has been an integral part of our success. Quebec, of course, has a strong dynamic center of Canadian research. I can cite lots of people. I won't start that. Brenda, is Brenda Milner here? Oh, she was on the guest list. Maybe she's not arrived. Brenda, of course, a world-famous neuroscientist well into her 90s now at the MNI. For over 20 years, we have had key fellows from the Quebec research community at CIFAR. Among those I'd like to acknowledge in particular are Pierre Fortin, who I saw earlier this evening. There you are, Pierre. Professor of Economics at the University du Québec à Montreal. Gérard Bouchard, distinguished historian and social scientist at the University du Québec à Chicoutimi. And Antonia Maioni, a political scientist at McGill University and recently appointed Dean of Arts at McGill, who serves as a member of the President's Research Council. 31 of our fellows and advisors come from Quebec, and 3 of them serve as directors of our research programs. And conversely, CIFAR brings to Quebec the opportunity to work within close-knit interdisciplinary groups where they can build collaborations with the best minds in the world. Our researchers come from top international institutions like Harvard, Princeton, Oxford, Stanford, the London School of Economics, the École Polytechnique, and many others. CIFAR has a long history of partnerships in the province of Quebec. Our current fellows hail from McGill, the Université de Montréal, Laval, Université de Québec à Montréal, Université de Québec à Chicoutimi, Concordia, and the Université de Sherbrooke. I'd like to single out the University of Sherbrooke as an example of the synergy between CIFAR and our university partners. The Department of Physics there is one of the strongest in Canada. Fully half of the members of its physics department are in CIFAR programs, either in quantum materials or in quantum information science. Louis Taillefer, distinguished physicist who you'll hear from later this evening, has been the director of our program in quantum materials and a CIFAR fellow since 1992, and a physics professor and Canada Research Chair at Sherbrooke since 2002. For more than 2 decades, CIFAR has been connected to the research effort at Sherbrooke, helping that university recruit talent and build a critical mass of expertise in quantum science. That investment received an even greater boost from the Canada First Research Excellence Fund, the new federal government program, through which the federal government awarded $33.5 million for research in quantum science at Sherbrooke. Now, CIFAR has 2 other mandates. The second is to support the next generation of research leaders. And this month, as I've said, we launched the new CIFAR Azrieli Global Scholars Program. That program will bring together outstanding early career researchers from around the world and connect them with the world's best in our research networks. It is a tremendous opportunity for young researchers at the very beginning of their careers to launch their careers to be able to interact with the world's best in their fields of study. We also work to connect our fellows with stakeholders who can benefit from that work. We regularly now hold briefings with senior government officials so they can learn directly from some of the most informed researchers in the world. And we're organizing similar opportunities for leaders in industry, community service, healthcare, and more. I was very pleased with the discussion that we had earlier today with CIFAR's board, which reaffirmed its desire to see CIFAR expand its role in convening the best minds in the world, not just in research, but also in policy and practice. And with this, we believe we are accelerating the ability for that knowledge and the insights generated by our researchers to have truly great impact on the world. You know, Louis Pasteur once said, what every researcher wants is just two things. He wants to make a great discovery, and he wants that discovery to benefit mankind. And that's what we expect of our 365 researchers. So tonight we will hear from three outstanding Quebec-based CIFAR fellows who are not only among the best in Canada, but they are amongst the best in the world. First, we'll hear from Louis Taillefer, how his research into the quantum properties of materials could lead to room temperature superconductivity and more efficient power transmission. From Yoshua Bengio, from the Université de Montreal, about how artificial intelligence developed within the CIFAR program that he leads will give rise to smart cars and perhaps new ways of discovering new medicines and many other applications. From Victoria Kaspi, about changes to what we know about how our universe was formed and how it is shaped today. Denis Thirion, our VP Research and Partnerships, will introduce these three distinguished researchers to you later on this evening. To do all that we do, we depend critically on the generosity of our supporters. I'd like to thank the federal and provincial governments of Quebec, of Ontario, of Alberta, British Columbia, and the federal government for their support, and the donors whose names I think we'll see on the screen this evening. Many are here tonight, and I'm grateful to you for making our research possible, and of course I've singled out some of them. It is now my very great pleasure to introduce Dr. Remy Quirion. Remy is Quebec's first chief scientist. In that very important role, he advises the Minister of Higher Education, Research, and Science, maintaining Quebec's position as a true leader in research at home and abroad. He also chairs the three Fonds de Recherche du Québec, the boards, and is a valued member of CIFAR's President Research Council. Remy is an eminent scientist in his own right, who has made many contributions to our understanding of Alzheimer's disease and mental health. In fact, as I recall, Remy, the very first thing I said to you was, you publish too much. Remy is a member of the Royal Society of Canada, the Order of Canada, and the Ordre National du Québec, as well as the 2003 recipient of the Wilder Penfield Prize, amongst many other honors. And most importantly, he is a friend and former colleague from our time at l'Institut de Recherche en Santé du Canada. His support and advice has been invaluable to the Institute. Once again, I want to thank every one of you for coming here this evening and for your support, and I hope you will enjoy your evening. Now, please join me in welcoming Dr. Remy Quirion.
Bonsoir et merci beaucoup, Alan. Bienvenue à tous les membres du conseil d'administration de l'ICRA. Bienvenue à tous les chercheurs associés avec l'ICRA. Et je sais que dans la salle, il y en a qui sont associés avec l'ICRA depuis presque ma naissance, je dirais. Aussi les jeunes chercheurs dans la salle associés avec l'ICRA, vraiment très, très important, tout ce qui est relié à la relève, et merci encore à la Fondation pour le don qu'ils ont fait. Souhaiter la bienvenue au nom du gouvernement du Québec, au nom de notre nouveau ministère. C'est vrai qu'on change assez souvent au Québec, donc on a encore un nouveau nom. Le ministère de l'Économie, de la Science et de l'Innovation. Et la ministre, Mme Dominique Anglade. Aussi, j'aimerais souhaiter la bienvenue au nom de l'autre ministère auquel on appartenait il y a quelques semaines, le ministère de l'Enseignement supérieur. et la ministre Hélène David. Donc, au nom des deux ministres et au nom des fonds de recherche du Québec et en mon nom personnel, bienvenue. CIFAR. Well, I think Alan mentioned quite a few things, but for me, what resonates is excellence, excellence, and excellence. This is number one. Partnership, number two. Mentoring, number three. C'est tous des mots qui sont tout à fait essentiels dans la mission des fonds de recherche du Québec. Et j'aimerais souligner ici ce soir la présence du directeur scientifique du Fonds Santé, Reynaldo Battista. Peut-être, Reynaldo, tu peux te lever pour que les gens... Donc, pour nous, au Fonds de recherche du Québec, comme pour l'ICRA, l'excellence, il n'y a pas de compromis à faire à ce sujet-là. Et comme ça a été mentionné par Alan, les chercheurs québécois qui vont présenter certains de leurs résultats de recherche dans quelques minutes, c'est certainement parmi les meilleurs, sinon les meilleurs au monde. Partnership. That's part of my mandate. Try to do partnership for the Fonds de recherche du Québec with various ministries in Quebec, various organizations in Quebec, various organizations in Canada, and various organizations globally. That's part of the mandate. And I always tell the colleague, Quebec basically is kind of a suburb of Beijing in terms of population. If we want to have impact, we have to partner. And we have to partner with the best in the world. And for us, CIFAR is among the very best in the world. At the moment, and I think Alan was very polite not to say that, but I'll say it, at the moment, the partnership is small. From the Fonds de recherche du Québec, we are a partner with CIFAR, but we really need to build on that when we compare what the federal government is doing, what Ontario is doing, and others. And I know there is someone from the cabinet here of Dominique Anglade, Marie-Paul Jensen, so certainly we'll be able to talk a little bit more about that in the coming weeks. Mentoring. Pour nous, au Fonds de recherche du Québec, environ 40% des budgets de recherche, environ 200 millions de dollars par année, va pour la relève, va pour les jeunes chercheurs. Donc là, le mentorat est tout à fait essentiel, tout à fait critique. Donc, le nouveau programme, l'ICRA, vraiment, il faut essayer d'imiter, nous, au Fonds de recherche du Québec, et créer un programme semblable. Alan already mentioned the partnership in the context of the large federal program with the University de Sherbrooke. I think in the phase 2, and there is many people here from the University of Montreal, from Polytechnic, from Sherbrooke, and from others. The role that CIFAR played in the preparation of the application that was submitted just a few days ago was amazing. And there I would like to thank my friend Denis Terrien, really was very much involved with the university in Quebec to try to build a proposal that would be highly competitive nationally and internationally. And, maybe I should not say it, but I say it anyway, even for those of you in the room, VP Research, even if it's not approved, your submission to the program at the federal level will do it anyway. All the work that you put into that, so working with CIFAR and working with us at the Fonds de recherche du Québec and the Quebec government will deliver. And I'm very happy that in the end, Quebec government said, yes, we really need to write very strong letter of support to put money on the table, and they did more, I would say, than I expected personally. So that's extremely, extremely good news. So I really wish you a very, very good night. You'll hear great science, and I look forward to working more closely in the future with CIFAR and all of you. Merci.
On a eu la nourriture pour le corps, et maintenant, c'est le temps d'avoir la nourriture pour l'esprit. Vous allez voir qu'on est gâtés pas mal pour le dessert. 3 chercheurs exceptionnels, des chercheurs le genre qui gagnent les prix là, les uns en arrière des autres. 3 exceptional leaders, all of them directors of CIFAR programs, which means that they are leading international teams of top scientists in the world in their area. And there are many team leaders in this crowd tonight, so you know that this really means something. C'est des scientifiques qui transforment le monde dans lequel ils vivent. C'est des gens comme eux qui font l'ICRA. Ce sont eux l'ICRA. And I will say this in English because this is very important. These people are CIFAR. Without them, CIFAR has no raison d'être. And as long as we attract in our organization people of that caliber, we have a role to play. And if ever we stop attracting that kind of people, then for us it's the end. So that's very simple. The first one will be Louis Taillefer, qui est directeur du programme de l'ICRA sur les matériaux quantiques. Il est à l'Université de Sherbrooke. Alan vous a raconté un peu tantôt le rôle, la relation spéciale qui existe entre Sherbrooke et l'ICRA. C'est unique au Canada. C'est l'université qui a réussi à utiliser le plus, de la façon la plus intelligente et la plus stratégique, l'outil que représente l'ICRA pour développer un projet. Alors, bravo Sherbrooke. Louis is director of the program on quantum materials. The expression quantum materials, which is known all around the world today, was actually invented by this program. This did not exist, the word quantum materials, until the group started talking about this. La biographie de Louis, écoute, Ordre national du Québec, Ordre du Canada, Prix du Québec Marie-Victorin, la médaille Herzberg, le prix Urgel Archambault. En tout cas, je vais en sauter un peu parce qu'on va être ici jusqu'à demain matin. Louis Taillefer.
Merci, Denis. Bienvenue à tous. Bienvenue à l'ICRA, my home. Ça fait depuis 20 ans, je fais partie du programme sur les matériaux quantiques. Vous ne savez peut-être pas c'est quoi un matériau quantique, mais ça va venir. Comme Denis l'a dit, le nom matériau quantique n'existait pas il y a 20 ans. Nous l'avons inventé et maintenant, tous les scientifiques savent ce que c'est. C'est la frontière de la science des matériaux où les propriétés électroniques sont le plus spectaculaires. Et peut-être le meilleur exemple de ça, c'est la supraconductivité dont je vais vous parler ce soir. So a superconductor is a metal that when you cool it down, it undergoes a phase transition, a very abrupt, sudden phase transition, as displayed here, where the resistance as a function of temperature, the resistance to electric current, goes abruptly to zero. And it's exactly zero. So the only formula I'm asking you to remember today is R equals zero. Very simple. So R is really absolutely zero, meaning that the conduction of electricity is perfect. So conductivity is infinite. So these words of perfect, infinite are rare in nature. But in this case, this is really the case. So much so that if you have an electric current going around a loop, just a wire, and you take off the battery and you just close the loop, that current will go on forever. Well, technically, I think we estimate 100,000 years. That's perpetual motion. This sort of almost magical property of superconductors has actually been applied in real technology. So today, the main applications are electromagnets, powerful electromagnets that enable things like MRI, l'imagerie magnétique dans les hôpitaux, la lévitation des trains, comme dans le maglev, ou la déflexion des particules subatomiques à CERN. But there may be other applications. The US Department of Energy estimates that by 2030, the demand on electricity in the US will go up by 50%. Globally by 100%. These are enormous increases for a system that's almost a capacity. So it is felt that some kind of revolution has to happen if that demand will be met. Some people think that that revolution will come from superconductors. A few years ago, Scientific American went through an interesting exercise in trying to come up with 12 really big events that would change everything. So they mentioned machine intelligence, which we'll hear about. They mentioned human cloning. They mentioned, of course, things like total nuclear warfare, polar meltdown, asteroid hits the planet, deadly pandemic, the more boring ones. And then, room temperature superconductors. Why did they put it up there? Precisely for this reason, that if you have that, the whole grid, which the Association of American Engineers regards as the single most important technological advance of the 20th century, the electric grid. That will be revolutionized. Now, the problem is that superconductors today is strictly limited to low temperatures. It's a low temperature phenomenon. We only have superconductivity at very low temperatures. Here I'm drawing the critical temperature below which you see superconductivity as a function of years. So it was discovered in 1911. Ça a été découvert dans le mercure, en fait, à 4 degrés Kelvin. Donc 4 degrés, c'est moins 273 Celsius. Très, très froid. On atteint cette température avec de l'hélium liquide. Et après, au fil des années, ça a monté un petit peu, mais pas beaucoup. And then came a revolution in 1986. The fastest ever awarded Nobel Prize for that discovery within 1 year, 1987, for a family of materials where the critical temperature shot up by a factor of 7 within a few years. And then, frustratingly, it stopped at halfway to room temperature. You see this bar there at 150? That's halfway to room temperature. That family of materials has sort of saturated there since then. So the question is, how can we improve on that? And from the perspective of a scientist, a research scientist, the question really is going back to the microscopic principles of what causes superconductivity. So at the microscopic level of electrons moving around in a metal, superconductivity is about the binding of electrons into pairs. It's sort of counterintuitive. But it's now very well understood that two electrons can pair if they're able to polarize the solid around them. So they have a negative charge, they polarize the positively charged ions, and that can then bring about another electron that follows and therefore forms a pair. So let's call this the electric force. It's the conventional force that's very well understood, in fact. Now, in 2008, discovery was made, so 8 years ago, of a new family of superconductors. So not the copper-based that I mentioned, but now iron-based superconductors. And in those materials, it was very clear that a new force is at play. Not the conventional electric force that we know and understand well, that works at minus 250 degrees, but something that works actually at higher temperatures. So you see in this diagram here, this is called a phase diagram. So we have temperature on the y-axis and concentration of electrons on the x-axis. This is something you can change by tuning the chemistry. And on the left, you have a phase that's magnetic. So what do we mean by that? We mean like the bar magnet on your fridge. That's a magnet. So this is a state that electrons can enter into. So there we have a magnetic phase. If you go a little bit to the right, then we have a superconducting phase. And superconductivity peaks where the magnetic phase ends. And that's a key. That's a key to tell us that actually the superconductivity comes from a magnetic force. It's not the sort of electric polarizability or susceptibility of the material that is important. It's the magnetic susceptibility that's important. So the magnetic force has been established in these family of materials, and it's giving a TC that's significant, very high. Still very cold from our perspective, but high from the perspective of superconductors. Just 2 years ago, another discovery in the same family of materials was made. This is very simple material, iron, selenium. But people found out, a group of scientists in China found out that if you make a single atomic layer of this stuff and you stick it on top of a substrate, you can double TC. And they achieved 100 Kelvin. This caused a sensation. And the understanding we have at the moment is that actually they're combining the two forces. The magnetic in the thin film, FeSe, and the electric in the more conventional substrate that seem to work together to boost, to get that factor of 2. Last year, a striking discovery that in just about the simplest material you can think of, hydrogen, which is a gas, as we know, if you pressurize that gas and turn it into a solid, for this you need pressures that are comparable to the pressure inside the Earth. Huge pressures. Only a few labs in the world can do this. If you pressurize hydrogen gas, actually technically it's H3S, it's hydrogen sulfide, but it's a gas of hydrogen. If you pressurize it, you make it a metal, it becomes a superconductor, and not only that, but it's the best ever superconductor. So we have 200 Kelvin. This is 2/3 of room temperature, you know. So there's an excitement at the moment. There's a sense where it is possible to have a room temperature superconductor. And so let me just mention one discovery made by a CIFAR team very recently in 2015, was published in 2016. I'm going back now to our copper-based superconductors, which hold the record, at least at room pressure. You don't have to apply enormous pressures. And here you see a phase diagram that sort of looks like the phase diagram I showed you before, where you have temperature and concentration. But the magnetic phase ends before the superconducting phase begins. So it's sort of different. And in fact, what's been the mystery in that field for the last 20 years is this thing marked with a question mark. There's some other phase, we call it the pseudogap phase, but might as well call it a dark phase or something. So what the hell is that phase? There's a lot of debate. And what the CIFAR team finally did, and that was enabled by a development in the production of very large magnetic fields, is that they used a huge magnetic field to kill superconductivity, to wipe it out, and then go and look at zero temperature, or very, very close to zero temperature, to identify the signature of the critical point where that mysterious phase ends. And that's just been done. And that gives us a new window on basically what's going on where the superconductivity is strongest. And we feel we have a hold on what is likely to be the force at play here. And all we need is a factor of 2. So that team, just to tell you a little bit how CIFAR has played a key role in this discovery, as in many others, is because of this chart here. It's because in our field of material science, you need 3 kinds of experts. You need people who make materials. And these are like modern-day alchemists. They're people they're geniuses who combine atoms and make new materials all the time. And so you need people who make materials. Then you need people who measure the properties of those materials, and there's many properties you can imagine measuring. You can shine light, you can apply large magnetic fields, large pressures, low temperatures, measure electrical properties, and so on, right? So you need these experimentalists in circle number 2 here. Finally, you need theorists who develop theories and model to really have a mathematical understanding of what's going on. And the key is to close that loop tightly and to have the best in the world work together on a long-term basis wherever they're from. And they're they're very likely not to be in the same place and not even to be in Canada, all of them. So you might have a Japanese materials expert and an American theorist with a Canadian experimental team. So the key is to bring these people together, and that's really what CIFAR does. And so in this particular discovery, I can mention that the groups that were involved were a group of materials experts recognized as the best in the field at UBC, pairing up with our team at Sherbrooke, doing the experiments with one guy called Cyril Proust in Toulouse, who's the best scientist for high field measurements. So the Toulouse National Lab has recently made a 90 Tesla magnet. It's right there. And 90 Tesla is just about the highest field you can produce in the world. 2 million times the Earth's magnetic field. So they've only had that for a year. This guy is the best guy to operate it, and he's been a member for 10 years of our program. So that team came together to enable that discovery. Okay, so where do we go from here? Well, we need to understand what's just been discovered more, so more measurements are needed. The theorists need to then model that and predict what knob to turn to get that factor of 2, and then deliver that mandate to the materials guys, who in the end are going to have to make the materials that superconduct at room temperature. It could be some kind of a substrate, some kind of a film deposit. It might be a combination of film and substrate, for example. So just to summarize then, I foresee a bright future for superconductivity. I've mentioned in particular how it could revolutionize the grid. And that here I'm showing an electric car because if all cars go electric in the next 20 years, imagine the increase on the demand of electricity. It's going to be enormous. That wasn't factored into the DOE estimate of 50%. That's one example of green energy, but we might think of others, like solar energy in the Sahara that you'd like to bring to Europe. At the moment, high power line, high frequency lines are not a solution. You need a DC superconducting pipeline underneath the Mediterranean to do it, for example. So enabling of green energies is one thing. Quantum computing might be involved. The quantum computer is the big holy grail of another program at CIFAR, and many proposals are on the table, but one of the promising ones is the superconducting qubit as the basis for a superconducting computer. And finally, just an analogy I'd like to make, because my gut feeling is that we cannot actually imagine what a room temperature superconductor would really do. It's a little bit like the transistor. In 1947, when it was invented, people were asking, well, okay, so what's that going to do for us? Well, they didn't know. I mean, they had no idea, right? They Googled 60 years later, right? So you have no idea. So the same, I think, will happen if you have a room temperature superconductor. And the analogy I like to make is between electricity and light. You can have a 100-watt light bulb, and you can have a 100-watt laser. You immediately know that there's something special about the laser. It can manipulate information in a very focused way. And that's because of something called quantum coherence, which means that all the particles, in this case photons, are doing the same thing. They have the same wavelength, they have the same phase. You want that coherence. Well, a superconductor is the quantum coherent form of electricity. And we don't have that at the moment. Well, we have it at very low temperatures. When we have it at room temperature on your table, I think a lot of bright young minds will find ways to use that. So I trust in that. And so let me close by saying that, repeating a little bit what Alan said, that we've just created a new institute in Sherbrooke called the Quantum Institute. Who would have guessed? And that comes in the wake of a major award from the federal government that came through this new program called the Canada First Research Excellence Fund, whose inaugural competition was last year. So very unusual thing. I mean, the federal government has, several $1 billion to offer. It launches a competition, one project per university. 60 projects were submitted. 5 were selected. 2 out of those 5 are on quantum materials. You might ask, well, why? The answer is CIFAR. The reason why those 2, one at UBC, one at Sherbrooke, The reason why they won, the reason why they got $100 million to do quantum materials research for the next 7 years is because of CIFAR. Because one of the important criterions was how well are you connected to the world? Well, we only had to say CIFAR. That was a demonstration. So thank you very much.
Wow! What can I say? Merci, Louis. Le deuxième plat va être servi par Yoshua Bengio, qui est co-directeur du programme de l'ICRA qui s'appelle Apprentissage automatique, apprentissage biologique. Yoshua est professeur à l'Université de Montréal au département d'informatique et recherche opérationnelle. I take for granted that you have all heard of Internet in this room. Well, CIFAR has nothing to do with that. Maybe not all of you have heard about deep learning. CIFAR has a lot to do with deep learning. That's a new paradigm for making intelligent, effective use of computer data in vision, in speech, in image recognition, in natural language processing. Deep learning has completely revolutionized the world of IT in the last small number of years, 2 or 3 years. And that is recognized all around the world as having been a CIFAR enterprise. In just a few years, the volume of business associated to deep learning has gone from the $1 million per year that CIFAR was putting in this program to several billions of dollars. La recherche fondamentale, ça ne change pas le monde, sauf que, comme l'annonce le dit. Yoshua est un des 3 mousquetaires qui sont associés à la création de deep learning. Et ça, c'est un consensus, ce n'est pas une opinion, c'est un consensus international avec Jeff Hinton et Yann LeCun. Yoshua a peut-être la particularité d'être celui qui a choisi de demeurer dans le monde académique, malgré les ponts d'or, comme vous pouvez l'imaginer, qui lui ont été offerts pour transférer on the dark side. Bravo, Yoshua! Il dirige un laboratoire qui s'appelle MILA, qui est le plus important laboratoire académique dans le deep learning. Et c'est un programme qui montre de façon exemplaire comment le monde de la recherche, le monde de la technologie se rejoignent à un moment donné, puis comment que le changement, la transformation de la planète s'effectue à partir de la base de la science. Yoshua Bengio.
Merci Denis, merci pour cette introduction. Welcome everybody. I'm going to tell you about AI. I'm going to tell you about deep learning. En fait, il faut que je rajoute quelque chose qui n'était pas dans mon plan. Nous aussi, on a inventé un terme. Deep learning vient de nos travaux des 10 dernières années. Et c'est un terme qui a pris une place qui était auparavant prise par un autre terme, neural networks. You may have heard about neural networks. And basically, deep learning is the modern way of neural networks. Okay, so let me move on about deep learning. So what is this about? First, I need to tell you a little bit about AI. How do we make intelligent machines? An intelligent entity, whether it's human or a machine, needs knowledge. And where is that knowledge going to come from? What we've discovered in the last few years is that to give knowledge to computers, we just let the computers learn from data, learn from examples. And this very simple idea has worked beyond expectations in the last couple of decades. And deep learning is the most recent instantiation of this, which is extremely successful. It has yielded breakthroughs first in speech recognition, then in computer vision, and now ongoing in natural language understanding. And we're working on health applications and many others around the world. So let me try to tell you more. First of all, a little bit of the history. So here are the three musketeers, les trois mousquetaires dont Denis parlait. J'aurais préféré qu'on mette Jeff Hinton en haut. Jeff est celui qui a démarré ce programme de l'ICRA à l'Université de Toronto. Et disons que ça se faisait un peu ce trio Montréal, Toronto, New York. The three of us were working on this challenge. We didn't know before 2006 how to make these neural networks deeper, how to have more layers. And thanks to the use of unsupervised learning, some new way of doing things, we for the first time 10 years ago, we managed to pass this barrier. And then in the later years, we found other tricks, and lots of researchers embarked on this, and then applications came years later. One thing I want to mention is that it's because CIFAR believed in us, believed in an area which 10 years ago was considered not promising, not fashionable, but that CIFAR and a few other people in our group, of course, believed could change the world, that this happened. It's because we collectively made these bets, because we believed in this fundamental research, which it wasn't clear where it would go, that we're today with the amazing applications that I'll be telling you about. And it's just the tip of the iceberg. What's going to come later is much more important. Okay, so it started after our scientific advances, which have continued at a pretty slow pace. We've started to see the impact in industry. And one of the first areas was speech recognition. I don't know if you ever remember using phone systems with speech recognition. It was terrible, right? And nowadays, it just works if you have the right systems. Most of the systems are pretty good now. It even works, ça marche même en français. OK? Sérieusement, j'étais vraiment surpris il y a à peu près un an quand je me suis dit, je vais essayer la version française du système de reconnaissance de la parole de Android. I was expecting it would not work because there's not nearly as much data for French as for English. Mais ça fonctionne, et même avec toutes sortes d'accents, etc. Donc, il y a encore des... Oui, j'ai un genre d'hybride franco-québécois. So, interestingly, this happened after about 10 years of stagnation of performance. So this curve shows over years the error rate, of speech recognition systems, and the little white circle is when deep learning got into the picture. Right, the next breakthrough came in computer vision. Actually, computer vision is, in a sense, much bigger than speech recognition because vision is such an important sense for us and for understanding the world. And it came with two important ingredients beyond what we had done for speech recognition. And these are very simple things: computing power and data. The computing power came thanks to GPUs, graphics processing units. Ces unités GPU qui, au départ, ont été mis au point pour les jeux vidéo. Il se trouve que ça fonctionne très bien pour les réseaux de neurones et pour les multiplications de matrices, qui prend le plus de temps de calcul. The other big element was data. Thanks to crowdsourcing, we were able to label lots more data, and it turned out to be very important. And so in the span of 3 or 4 years since then, the error rate has gone down so that on several benchmarks, we're now essentially at the same level as human performance, which I couldn't have believed that just a few years ago. So this has, of course, attracted a lot of attention from the media. It started about 2012. And not only the media, quickly big companies like Google and Facebook realized that this could be very, very important for them. And And they started fighting to buy talent, to buy my colleagues, Jeff and Jan, and to buy companies like DeepMind, a British company which had basically two dozen PhDs with deep learning expertise, mostly coming from our labs, and not making any money, but they bought it for 500 million pounds actually. And then, of course, a lot of other companies jumped in, and some were already there, like IBM and Microsoft, and many other came into this, including nowadays companies like Qualcomm who want to build chips. So the thing we've seen with GPUs is nothing when they start building specialized hardware to run these neural nets. We're going to be able to cram a lot more knowledge into these machines. So let me say a few words about why deep learning is working. The central idea is to learn representations. The classical machine learning is going directly from inputs to classifications, predictions, the thing that we want the system to perform. These neural nets, and especially the deep ones, they introduce intermediate levels of representations. And we can try to understand what these do. So in the picture here, each little square represents what a particular artificial neuron likes. And we see these three levels. So in the lower level, these artificial neurons like to detect edges in images. And higher up, we have units that like to recognize parts of your face, like part of a nose or an eye. And these are obtained by combining the detections made at the lower level. And then again, higher up, we see units that like to detect particular kinds of faces, and they combine the parts together. And that's just one of the ways, but the important idea is that there's this compositionality. In other words, composing pieces together, and that gives what computer scientists love, which is an exponential advantage. And so one of the things we've proven recently is that you can represent very rich functions by doing a series of these transformations, extracting these detectors that are learned. You can represent functions that are more abstract in some sense. And that's what allows these machines to generalize better to new cases, which is what we want machine learning to do. Another nice thing about thinking in terms of representations is that we can play very fun games. So instead of just thinking about representing an image, we can think about representing different kinds of things, like images, but also text or speech or any kind of information. And in this example, which is Google image search, what they've done is they're learning a representation for queries for a sequence of characters, which is in the same space as a representation for images. So they're learning two transformations, two functions, one that goes from an image to these 100 numbers representing the semantic content of the image. And they also learn a function that goes from a sequence of characters to the same 100 numbers, such that things that mean the same thing, that talk about the same topic, end up close to each other. So dolphin will be mapped to something close to the image of a dolphin. And other images of dolphins, even though they might look different, will end up near each other. And that's how they are able to answer your queries and find images that mean something that's related to what you typed. And of course, you could go in the other direction, and given an image, you can find sequences of characters that have a similar meaning. One of the things we've done in my lab in particular is combine this representations for images and representations for natural language. And one of the most impressive recent results we obtained is having a system that takes an image as input and produces a sentence in English. So here you see on the left this image of a woman in a park, and the computer produces the words, "A woman is throwing a frisbee in a park." What you see in the second image is where the computer is putting its attention while it's saying the underlined word. So here, when it's saying frisbee, it's actually paying attention to the part of the image that contains a frisbee. In the second image, it's seeing this image with a dog, and it's saying a dog is standing on a hardwood floor. And when it says dog, it's looking at the image of the dog, right? Now, it still makes a lot of mistakes because we didn't have that much data to train it. So you can see some of the examples of mistakes, which are very informative and helps us to understand how to improve these systems. So for example, the second one, you see this image of a woman, and the computer says, a woman holding a clock in her hand. So obviously it's a mistake, there's no clock. But if you look at the pattern on her shirt, when the computer says clock, it's actually looking at that pattern. It's like circular, and there's some letters there, so you could confuse it for a clock. Right? Sometimes it makes really crazy statements, like for the third one, it says, a man wearing a hat on a skateboard. Well, I have no idea where this is coming from. But if you train it with a lot more data, then you can get these kinds of results. There's a video. So now the computer
Is there a baby?
is going to answer questions.
Yes.
What is the man doing?
Typing.
Is the baby sitting on his lap?
Yes.
What you see are the
Are they
scores
smiling?
of the main answer, the
Yes.
high-scoring answers that it finds.
Is there a baby in the photo?
Yes.
Where is the baby standing?
Bathroom.
What is the baby doing?
Brushing teeth.
What game is being played?
Soccer.
Is someone kicking the ball?
Yes.
What color is the ball?
Yellow.
What game is the dog playing?
Second answer was green.
Frisbee.
What color is the dog?
Black.
Is the dog wearing a collar?
Yes.
What is the cat sniffing?
Banana.
Where is the cat?
On bed.
What color is the cat?
Black and white.
What color are the bananas?
Green.
All right. Let me tell you a few words about where this is leading us. And one of the hottest areas right now is to go beyond the traditional pattern recognition ability of these systems and into higher level cognition. And we're still making baby steps. So what you see here is these recurrent neural nets, special kinds of neural nets, that are able to read a piece of text and answer a question. But this time, the answer is not obvious, and you have to reason. You have to combine multiple facts together. So let me read this to you. The computer reads this. Sam walks into the kitchen. Sam picks an apple. Sam walks into the bedroom. Sam drops the apple. Where is the apple? Well, if you follow what I said, you should know that it's in the bedroom. And you can't just look for words that are names of places, because you could say kitchen as well, right? So some kind of reasoning is necessary. Now, I'm going to show you a video of showing, again, these kinds of image-to-text translation that's been done at Facebook from my co-director, Yann Lequin. And you'll see something pretty nice for blind people who can now get a sense of what's in images. Want to start?
Our goal is to build intelligent machines to help people in their daily lives. What makes us intelligent is our ability to learn. And this is what we're trying to reproduce in machines. To some extent, we get inspiration from biology. What we can do with current technology is build networks of simulated neurons on the order of magnitude of the brain of a mouse, let's say. So the way we train our machine, we show a bunch of images of, say, breeds of dogs, and for each image we tell it what it is.
We want the machine to be able to learn to perform the tasks. The more we show them examples, the better they get.
And what's very interesting is that after a while it can do this with a new dog it's never seen before. It's able to exhibit superhuman performance on a particular task. So how can we help people's life with this?
Friends 937. Newsfeed. Lindsay Russell updated her cover photo yesterday at 10:29 p.m. This image may contain outdoor, cloud, foliage, flattened, tree. This image may contain 6 people. Child. Close up. Like. One or more people. Jewelry. Smiling. 19 likes. 3 comments like.
Now I can see the picture in my head. Like, yeah, you shouldn't have been that close up. Like, now I can say it.
Oh my God, I love it. You have no idea. This is amazing.
That whole saying of pictures being worth 1,000 words, I think it's true, but unless you have somebody to describe it to you, even having like 3 words just helps flesh out all the details that I can't see.
I feel like I can fit in. There's more I can do.
I can just call my mom like, yay, I seen your picture. And she'll be like, what? She was like, how you see it? Because my phone read it to me. It's new. I'm going to mess with my mother head so much.
In the future, we'll be able to give a complete description of the image.
Are the 2 people happy? Are they sad? Are they holding hands with one another? It's this kind of comment that a human would make.
We have systems in the lab that are able to do this, and they will be deployed over the next few years. Artificial intelligence systems are going to be an extension of our brains, the same way cars are an extension of our legs. They're not going to replace us, they're going to amplify everything we do, augmenting your memory, giving you instant knowledge, and they're going to allow us to concentrate on doing things that are properly human.
Right, so sur cette note positive, je voudrais juste clore avec quelques mots sur qu'est-ce qui s'en vient. Et en fait, je dirais la même chose que Louis, c'est-à-dire qu'une grande partie de ce qui s'en vient, on ne sait pas vraiment parce que ça va prendre des jeunes qui réfléchissent, qui vont utiliser ces découvertes-là pour changer la société. Mais il y a des choses qu'on peut voir tout de suite assez facilement. One of the areas that I think is going to be very transformative is how we interact with computers. When computers not only understand the speech and transform it into words, but really understand what those words mean and can act accordingly, the way we deal with computers, with machines in general, is going to be completely transformed. And it's not just going to influence us in rich societies, but all over the world. Because once you have the recipe for this, it could be used for very cheap anywhere. And similarly, I think we're going to have amazing effects on society through the changes in healthcare. So what do I mean by this? What these machine learning algorithms can do, if we provide them with the data actually exists, it just needs to be put together in, centralized, is the ability for computers to interpret your medical information and help doctors take much better informed decisions. Right now, for example, we're collecting these genomic information, 2.5 million base pairs, for example, and a doctor can't look at all of these things to figure out, what's the best treatment for you. So we need computers to help us and predict what's the best treatment or our set of treatments for you. Another area which you've heard about is self-driving cars and robots in general. All of these heavily use deep learning. For now, it's mostly for the computer vision, but also for taking decisions and planning and so on in the future, even more than it is now. So as I said, these are just the things we can envision right now, but I'm sure people following us will have ideas for things we're not even thinking of right now. Thanks.
Oh, merci, Yoshua. There are 3 key words at CIFAR that define what we are: excellence, global, and impact. And you see what we mean by this in the talks tonight, quite a bit. Alors, le dessert du dessert, aujourd'hui, ça va être ma collègue de McGill, Victoria Kaspi, qui est Howard Webster Foundation Fellow à CIFAR et directrice en devenir du programme de cosmologie et gravité. Elle est professeure à McGill, donc au département de physique, où elle est chaire de recherche du Canada et chaire Lorne Trottier. Merci Lorne pour le support toujours. Many of us have been quite proud last October that Canada got a Nobel Prize in Physics. Art McDonald has been associated with CIFAR for decades. We have all heard and we have all been fascinated by the story on gravitational wave just a small number of weeks ago. There are some CIFAR fellows that are centrally involved in this story. The bio of Vicky is like a poem when you read this, right? Erzberg Medal, Stacey Prize, Killam Prize, Prix du Québec Marie-Victorin, Prix Urgel Archambault, Prix Erzberg, le top que vous pouvez avoir au Canada en sciences. La première femme à gagner le prix Erzberg. Maybe Nobel someday, who knows? No pressure, Vicky. Vicky Kaspi.
Et c'est un grand plaisir d'être ici ce soir. Et je vais vous parler d'une des questions que nous attaquons dans notre programme de CIFAR. Quelle est la nature de la gravité? What is the nature of gravity? Now, a lot of us think we know about gravity. It's what makes things fall. It's what makes you get down the ski hill. But, really, a physical understanding of gravity first came from this gentleman here, Isaac Newton, way back when, hundreds of years ago. And we all know the story of him sitting under the apple, getting hit by an apple, and suddenly realizing, oh, it's gravity. But what was that really about? It was about, and the reason that the theory of his gravity theory was called, universal law of gravitation, universel, was because what he put together was that the falling of that apple was telling us something very important about the reason we have planets in orbit. Two totally different ideas. He connected them. He realized with his cannon analogy that if you fire the cannon, yes, the cannonball will eventually fall. And if you fire it harder, the cannonball will fly even further. But if you fire it really hard, it will encircle, it will go all the way around and keep falling and falling and falling in what we call an orbit. And it was this realization that puts everyday objects together with the cosmos and explains why planets are in orbit around the sun. And this was our understanding of gravity, really until the 20th century. There's a classical picture, beautiful in many ways, but doesn't answer really simple questions like, why? What is this magic property of large masses that makes things fall toward them? Why? Simple kid question. And really, this classical picture of, and mathematically fairly simple theory of Newton, it was displaced. Revolution occurred in gravity in the 20th century thanks to Albert Einstein. Got mathematically a little bit more complicated, but he introduced the idea of relativistic dynamics, objects moving relativistically. And what does that mean? What he explained was that gravity, the reason things seem to fall, was purely geometric. He envisioned space-time as malleable, deformable. Here, it's represented by this two-dimensional surface, these lines that you see that are being deformed by mass. In his picture, in his understanding, mass deforms space-time, and he saw space as something you could stretch, and time is part of that. That's what the relativity is about, that you could stretch space-time, and that's exactly what mass does. It made gravity be something that is intimately entwined with geometry. And this picture, this different explanation, it's been around for, since he postulated it. And yes, person of the century, wow. But in science, and I feel really strongly about this, it's not about being a rock star. It's about being right and about being empirically verifiable. And so we don't just accept because he has great, he looks amazing, and brilliant theories in principle. You have to test them. And so we ask the question, was Einstein right? We do experiments to verify his theory. And even nowadays, we're going beyond that. We're asking, can we go beyond Einstein? Can we understand gravity at a level that even he didn't quite understand? That's part of our gravity and cosmology program. Can we unify it with other fundamental forces? And I think that he would have been thrilled. He would have loved to see the sort of work that we're doing in CIFAR. He was somebody who really enjoyed this interchange between experimentalists and theorists. And just after dinner, I have to show you this. I don't know if anybody recognizes it. That's the Hollywood actor John Malkovich being Einstein. And I ran into that on the accident on the internet, and I just had to show it to you. I thought it was so funny. Now, testing models of relativistic gravity. This is what we do. This is what we want to do. Was he right? In the solar system, in any environment that you're used to, the effects of general relativity are so tiny. They're minute. They're tiny perturbations on the physical laws that Newton saw. So yes, when he was alive, there were tests of general relativity, but they were all really difficult things to see and to measure. Tiny little effects. But today we know of parts of the universe where we can test general relativity, where it really matters, where Newton's classical dynamics breaks down very, very quickly. And we feel that if you're going to believe in this theory, you would better test it where it really matters. And there's two environments that we know of that are observationally accessible. One, the first one, I hope you can see, it says neutron stars, and that's the area of research that I do and some of my colleagues in CIFAR do, and those have been observable now for since 1967, really. And the other is black holes, and those are just starting to become truly observable. I'm going to tell you about both of them. So first of all, neutron stars. So neutron stars, and that's actually a little movie that would be good if we could start that up. So neutron stars, these are, this type of neutron star is called a radio pulsar, a pulsar. This is not a star that is just shining with, as you could see with your eyes. It's a star that is rotating, in this case about an axis that's vertical, and that has two bright beams coming out of its magnetic poles. And these are like cosmic lighthouses. So each time one of these stars rotates, that beam flashes toward Earth, and we receive a burst, a pulse of light. And actually, unfortunately, these types of stars, these radio pulsars, a form of neutron star, they're really compact. They're only about 20 kilometers across. And at interstellar distances, the distance of the galaxy, these things are way too small for any telescope to be able to resolve. So I have to show you only a cartoon. So I'm sorry about that, but that's what we understand is going on. But what you see, so we can't actually see these neutron stars in this way. What we see is the light from them turning on and turning off. So what we actually detect, this is the light coming on and off, over and over and over again. And in the bottom slide, what I'm showing you is some actual data from a telescope where you can see many, many of these pulses. This is what we observe. We digitize it with computers, we record it, and we analyze it with sophisticated algorithms. Now, what are these objects? What are these neutron stars? So we call them cosmic lighthouses. And what they represent, what they are is very massive stars. So about 40% more massive than our sun. And in case that's not intuitive enough for you, because not a lot of people are familiar with the mass of the sun is. But if you could take 500,000 planet Earths, okay, and take all that matter and crush it into a sphere of diameter 20 kilometers. So 500,000 Earths crushed into 20 kilometers. And you'd understand then this is a very, very dense object. So the density here is the highest in the universe that you can actually realize apart from in a black hole. And yet we can observe these objects. We know of 2,500 of them around the sky. This is something that we're doing a lot of. And you can imagine that there's a very high density. So if you could go up to a neutron star, and I don't recommend this, but if you could go up with a teaspoonful and just scoop a little bit of a neutron star, it would weigh 1 billion tons. So this is not like matter that we're used to here on Earth. It's not matter we can ever hope to produce in a terrestrial laboratory. And in fact, the nature of this kind of matter at ultra-high densities is really unknown currently to physicists. It's one of the interesting questions. How does matter behave under those extreme circumstances? And if those things aren't, exotic and weird enough for you, some of them rotate really, really rapidly. So the one I'm showing you here is pretty slow, but the fastest one we know of, which by the way was discovered on supercomputers at McGill University by my research group, rotates 716 times per second. So it's hard to imagine that, but it's faster than your blender, okay? Faster than the kitchen blender. And I should also say, these objects, for some quirk of nature we don't fully understand, are most easily observed not with optical telescopes that you could hope to look through, but with radio telescopes. And so the data that I'm showing you is actually radio waves from outer space detected using large radio telescopes. And here are some of the pictures of the radio telescopes that we use. On the left there, that's the Green Bank Radio Telescope in West Virginia. That's a 100-meter aperture. That's 2 buses down there in a building, just for scale. Another one that we use is the Arecibo Telescope in Puerto Rico. It's 300 meters across. This is a 3-story building over here. That's a 3-story building, and that's a catwalk you can walk up if you're crazy enough to do it, which we were. And here's actually a picture of us somewhere at the top of the feed structure there, several hundred feet above the surface. And some people ask me, is it scary to do that? And the answer is yes, terrifying. But this kind of science, with these radio telescopes, we sample the data very, very rapidly, collect huge data sets, and then cart them off to supercomputer centers. And major neutron star searches that we're doing currently at these radio telescopes are being processed on Compute Canada supercomputers, including the Gilliman one located at McGill University. As part of this sort of science, we collect huge, when I say huge, the search with Puerto Rico is we're collecting a total of 1 petabyte of data. So this kind of science also has a lot of applications for big data management, data visualization, and sophisticated, efficient computer algorithms. Now, I brought with me a few, just to get you in the spirit of this, to understand how fast these things are rotating, some sounds from pulsars. The first one is a slow pulsar, and you can go ahead and make that sound. So you take the output of a radio telescope, it's radio waves, amplify it and plug it into a speaker, and you can hear the sound of the pulsar. So this one, it's about 0.7 seconds. And each one of those is the rotation of the star. You hear each time that star is turning. And that's a typical one. Now the next one is a little faster. That's 11 rotations per second. And what you hear is something amazing. Sometimes the pulses are there. Sometimes it skips a beat, but then it always comes back in phase. The period between these pulses is very, very fixed. And I'm going to come back to that point. And the last one, this is one of the fastest rotators. And now it's in the audio range. The beats, your brain cannot separate one beat from the other. You're hearing a musical tone that doesn't exactly fit on the musical scale because it's at a 642 hertz. But this is how fast it's rotating. You can't even hear the individual beats. And sometimes we talk about the music of the cosmos. Pulsars provide that spectacular music. Now, one thing I want to say is that I'm hiding from you an important fact about these objects, which is why I'm dwelling on them so much, is that the time between pulses, this is this period that we talk about, the time between successive pulses, it actually can be measured with extreme precision. So that the period of this pulsar, the time between these pulses, is actually this value, here with 15 decimal places, and the number in brackets at the end here is the uncertainty, is the error bar on the last digit. Okay? Now, you have a very heavy object that loves to rotate. It's hard to make it jiggle around. It's an incredible clock. You have this fantastic clock at interstellar distances. This allows you to do spectacular physics experiments that lets us test all sorts of things about gravity. Sometimes one of the beautiful things about doing search is you find amazing objects. You find binary pulsars. That's a pulsar orbiting another star. And if you start up this movie, you're going to see, first of all, this is a movie of a double pulsar binary. We know one of those. We have two pulsars orbiting each other. And in this case, they're orbiting every 2.4 hours. So you think about the Earth going around the sun once a year. These things are orbiting each other really, really fast, once every 2.5 hours. And because they're such perfect clocks, we can observe these pulses with great precision and measure very rapidly deviations from Newton's law and test Einstein's theory of general relativity and even test alternative theories to gravity because general relativity isn't the only one out there. Most of these binary pulsars are not double pulsars. There's a neutron star, a pulsar, and some other star. And here's where we come to gravitational waves. If you think about a binary pulsar system, and here you see the binary and the magic green grid that you have there that's showing the distortion of space-time that's predicted in general relativity by Einstein, you see that if the binary is stationary, you have the same distortion where the mass is. But then, and if you go ahead and start the movie, as you have these things orbiting each other, that distortion is constantly changing space-time. And those changes get propagated outward, and that's what we mean by gravitational waves. So what you heard all about LIGO and about the detection of a double black hole system, I'm going to talk about that in a second. The point is you have motion of very heavy objects distorting the fabric of space-time repeatedly over and over again and sending out gravitational waves, which actually removes energy from the binary system. So it causes those two objects to coalesce eventually. And the first measurement of this sort of coalescence, or not the coalescence, but the leading to it, was actually awarded a Nobel Prize to Joseph Taylor in 1993. That was my PhD supervisor. What he measured was the decay of an orbit of a binary pulsar system. You can see the data points there perfectly following general relativity. If Newton were right, they would have lined up on this line here. So totally huge, huge effect. The error bars there are included. So now fast forward, so that was back in 1993, the Nobel Prize for verifying Einstein and seeing that there's gravitational waves indirectly by seeing the decay of an orbit, but not detecting those gravitational waves directly. And it took until now, 2016, to actually be able to measure those gravitational waves directly with LIGO, the Laser Interferometric Gravitational Wave Observatory, 2 interferometers with powerful lasers, one located in Livingston, Louisiana, and the other across the continent in Hanford, Washington. Very sophisticated instruments. And we're very proud to have CIFAR members also involved in this kind of project. What they detected, as you all heard about, were 2 black holes coalescing, something that you could never hope to observe with any telescope. There must be lots of these things going on in the universe, but they don't produce any light. And so this is a computer simulation of these 2 black holes. You can see the distortions in space-time cause this strange phenomenon around them of sort of, we call it gravitational lensing of the background stars. And what you can see is the actual data here from the 2 LIGO observatories, one in Louisiana and one in Washington, with this characteristic signal, exactly what you expect, and exactly as predicted by theorists. In fact, from that signal, the exact same signal across the continent, you can measure the masses of those 2 black holes. And, there's one thing, it's wonderful to be testing these kinds of advanced theories, but it's also really beautiful to be able to communicate this kind of science to the public. We have There was quite a bit of press around this, and one of the movies appeared in the New York Times was actually made by members of CIFAR collaboration. These are coalescing black holes. You can see again the repeated distortion of space-time, and there they've coalesced into a single black hole. Now, one of the next frontiers, and this is where neutron stars now merge with the sort of science that LIGO is doing, what we believe the next sort of source that LIGO is going to be able to detect. Maybe they'll detect lots more merging black holes, but another thing they could detect is a neutron star merging with a black hole. And this would be really spectacular because you have matter there. A black hole, there's no matter. It's a very clean system. If you take a real hard object like a neutron star and you merge it with a black hole, you have matter there that can then produce light that you could observe not only with LIGO, but then also with the telescope and learn so much about that matter. So I said we don't really know the nature of matter at these extreme densities in neutron stars. Well, here's a brand new way to understand that kind of matter by detecting a merging neutron star a black hole system and then simultaneously observing it with a regular kind of telescope, like a radio telescope or an optical telescope. And this is a movie, and you can start the movie, a simulation done by, let's go back to that. Oh, it's over here anyway, yeah. It's a simulation being done of a neutron star just before merger with a black hole, where the neutron star gets tidally shredded by the black hole, and all that unbelievably high density matter gets spread out, and we're predicting and trying to calculate now what the optical or radio or X-ray signature of this will be, and we will try and observe it with other telescopes. That's something we're working hard on in the CIFAR program. And just the last thing I thought I'd mention is that there's another connection between all these topics. The pulsars that we have been studying to test general relativity can also be used as detectors of gravitational waves. So there's many different ways that these things connect. And the CIFAR program is so wonderful for bringing so many different people together. But the idea here is that using radio telescopes around the world, we can observe many, many pulsars in the sky and detect gravitational waves that we think are passing, that theorists are predicting are passing through our galaxy at all times, and look for changes in the clock-like behavior of these different neutron stars. And we look for correlations on the sky, so some clocks are moving a little slower than other clocks. By comparing the clock-like behavior of all this ensemble of neutron stars around the sky, we're hoping to detect gravitational waves. In this case, not from regular merging black holes like LIGO's doing, but from merging supermassive black holes. And you say, what's a supermassive black hole? That's kind of scary sounding. Well, it turns out every single galaxy in the universe contains a supermassive black hole. The Milky Way, our own galaxy, has a supermassive black hole at its center. And when these supermassive black holes happen to meet, when galaxies happen to collide, and this happens all the time in the universe, those supermassive black holes will merge and produce gravitational waves. And so this is a movie of two galaxies, each with its own supermassive black hole at its heart, about to merge. Whoops, it didn't merge. Oh, over here it's merging. This one does as well, okay. So here come those galaxies, and shortly we're going to zoom into the centers where those supermassive black holes are. And there's our familiar green grid to show the distortion of space-time due to that huge amount of matter, 1 billion solar masses. And as they orbit each other, as they collide, gravitational waves get propagated throughout the universe. You're going to see, the movie's running a little slow, but so these gravitational waves move outward, they propagate throughout the universe, except in this movie, they're being beamed directly at the Milky Way, which is silly. But anyway, and they arrive here on Earth, so these giant radio telescopes can observe the pulsar, and as space-time is distorted by the gravitational waves from supermassive black holes, we are hoping, we haven't done this yet, but this is one of the projects we're working on, that we'll see the deviations in the ticks of the pulsar clocks around the sky and be able to infer the presence of those merging supermassive black holes. Radio pulsar timing tomorrow. Thanks to the CIFAR program, we've been able to bring together researchers from around the world in one of the most exciting projects in radio astronomy today. It's going to be fantastic for detection of gravitational waves through this method that I've just described. It's wonderful for testing general relativity using relativistic binaries. It's the CHIME radio telescope that we're building in Penticton, British Columbia. We received large grants from the Canada Foundation for Innovation. And that might not look like a radio telescope to you, but it's a very clever geometry for a telescope. Unlike a circular telescope that I showed you, which can look at a tiny piece of the sky at once, in this geometry you can look at a huge swath of the sky at once. And so just to set the scale here, that's 100 meters by 80 meters. So this thing has an area of six hockey arenas. And in fact, this is a picture of our team standing in the axes of these different cylinders. You can see them here. That's for scale. And the idea here is these reflectors are going to bounce radio waves from the sky up onto the axes, which are going to be populated with 2,048 antennas. 2,048 antennas, and all of those signals are going to be combined together and processed in order to make images of the sky and also study very rapid variations in the sky in radio waves. And if you calculate what this data rate for this telescope is, you realize it's not just a telescope, it's a sandbox for testing very high-speed digital signal processing. 1.6 terabytes per second of data are going to be flowing through these antennas and into our supercomputer to process that. That exceeds the global data rate for mobile phones. So all in one place here in Canada is a very creative kind of telescope. In fact, we were actually used as advertising for AMD for their GPUs that we're going to be purchasing to build this supercomputer out in Penticton. And anyway, to close, I've given you a flavor for some of the big questions that we're attacking in our cosmology and gravity programs, part of CIFAR. I've only had time to touch on a few of them, but the CIFAR program has been really central to this kind of advanced research that also has some pretty significant technical spin-offs. And so thank you very much for your attention.
Well, now you know why we're so passionate about CIFAR. Every time I attend one of these presentations, I feel that it's very stimulating, it's very humbling, scary, and I'm going to go to bed tonight again. I'm going to have a hard time going to sleep. I'm going to see all sorts of black holes. And my iPhone will be talking to me. So I need my glasses. Okay, so, well, I want to thank all of our speakers for those fascinating talks. One of the most rewarding things about being part of CIFAR is the chance to be exposed to our fellows' cutting-edge science. The questions they are answering, questions about the nature of the universe, about artificial intelligence, about harnessing superconductivity, and more, not only teach us about the world, but are also helping us to make the world a better place. J'espère qu'après tout ce que vous avez entendu ce soir, vous êtes aussi impressionnés que moi je le suis. Je vous encourage à participer à l'ICRA that's the marketing part, en devenant membre de la communauté de donateurs de l'ICRA appelée le Cercle du Savoir. Comme l'a mentionné Alan, c'est grâce à la générosité de bienfaiteurs que le travail de l'ICRA est possible. On offre régulièrement aux membres du Cercle du Savoir l'occasion d'interagir avec les chercheurs internationaux talentueux de l'ICRA. Pour savoir comment devenir membre, n'hésitez pas à venir me voir et à vous adresser à tout représentant de l'ICRA. The Knowledge Circle members regularly receive opportunities to engage with CIFAR talented international researchers. So please talk to me or anyone from CIFAR about how to become a member. Encore une fois, je vous remercie de votre présence ce soir. J'espère que la soirée vous a plu autant qu'à moi. Au revoir. Good night.